For a limited number of AB mixtures, there is a linear relationship between the partial pressures PA and PB and the mole fraction XA of A and XB of B in solution. Such experimental observations are highlighted here for the case of benzene and methylbenzene, also known as toluene. On the graph shown on the left-hand side, we see that for all methylbenzene mole fractions between 0 and 1, the partial pressure of either component increases with the mole fraction of that component in the mixed liquid phase and is equal to the vapor pressure of the pure component when the second component is absent. So, the vapor pressure of methylbenzene increases from 0 to about 22 torr as the mole fraction of methylbenzene in solution increases from 0 to 1. Similarly, the vapor pressure of benzene increases from 0 to about 76 torr when the mole fraction of methylbenzene decreases from 1 to 0, that is when the mole fraction of benzene increases from 0 to 1. These observations can be expressed mathematically as PA equals XAL times PA star and PB equals XBL times PB star. This relationship between the partial vapor pressure of a component above the solution, the mole fraction of that component in solution, XAL or XBL, and the vapor pressure of the pure component, PA star or PB star, is known as Raoult's law. A photo of the Swiss scientist Raoult is shown on the right-hand side. Raoult's law should not be confused with Dalton's law, which relates the same partial vapor pressure of a component above the solution to the total vapor pressure and the mole fraction of that component in the vapor phase. The total pressure, P sub T, above the solution is equal to the sum of the partial vapor pressures PA and PB. And using Raoult's law is written as PT equals XAL PA star plus XBL PB star. This equation suggests that the total pressure should also be a linear function of the mole fraction of either component in solution. We see that this is indeed the case for the benzene-methylbenzene solution, as the total pressure decreases linearly from 76 torr when methylbenzene mole fraction is 0 to 22 torr, the vapor pressure of pure methylbenzene, when the mole fraction of methylbenzene is 1. Raoult's law can also be used to further modify the expressions of the chemical potentials μA liquid and μB liquid, since Raoult's law allows to relate PA over PA star to XAL, PB over PB star to XBL. So, for solutions where both the solvent and the solute obey Raoult's law, the chemical potential of the solvent and the chemical potential of the solute can be expressed in terms of the mole fraction of that component in solution. Specifically, we get μA in the liquid state equal to μA star in the liquid state plus RT times the natural logarithm of the mole fraction of A in the liquid phase in solution. Similarly, the chemical potential for B in the liquid phase is equal to the chemical potential of pure B, that is μB star, in the liquid phase, plus RT times the natural logarithm of the mole fraction of B in solution. This very important relationship implies that the chemical potential of A in solution is always lower than that of A in the pure state, since Mole fractions are always less than unity, hence their natural logarithm is negative. This conclusion will have very important implications for the concept of osmotic pressure and for the diffusion of solute and solvent in non-equilibrium systems. Raoult's law indicates that for some mixtures, the reduction in vapor pressure from PA star to PA and PB star to PB, and the reduction in chemical potential from μA star to μA and μB star to μB is independent of the nature of the species and is only a function of the composition of the solution. The simple thermodynamic behavior of solutions, where all components follow Raoult's law, has justified the calling of such solutions ideal solutions. Note that for a solution to be ideal, all components must follow Raoult's law over the whole composition range. Over the next two slides, we will learn how Raoult's law leads to a very simple formulation of the Gibbs energy of mixing and to the remarkable thermodynamic properties of ideal solutions.